Welcome to the Unit 8 Section 4 video on transformations of quadratics. A parent function is the simplest function with the defining characteristics of the family. The quadratic parent function is f of x equals x squared. Any quadratic function with a different rate of change, a vertex other than the origin, and/or opening downward is a transformation of the parent function. Recall the vertex form of the quadratic equation. It gives us the location of the vertex, and x equals h gives us the location of the axis of symmetry. So let's talk about quadratic transformation rules. We are going to use vertex form to determine what transformations occur to the parent function. So to do this, we're going to look at all the pieces of vertex form, starting with the h value. You have a horizontal translation to the right if h is positive. So, for example, it would look something like x minus 3 quantity squared. Now, you may be thinking there's a negative in front of that 3, so 3 is negative, right? Well, if you look at the form up at the top here of your vertex form, negative is just a sign in the form. It's an operation. You're subtracting that h value. And the value that you are subtracting is 3. So h itself is positive, but in the form, it's going to look negative. That is a horizontal translation to the right. You can also have a horizontal translation to the left when h is negative. And in this case, we would have x minus negative 3, which would give us x plus 3 quantity squared. So it's going to look positive, but in reality, h itself is negative, and we have a translation to the left. Now, translations up and down are a little less confusing. If k on the end of your function is positive, then you're translating up as you would normally expect. So it would look something like x squared plus 5. If k is negative, then you have a translation down. In this case, it would look like x squared minus 5. So whatever that last little ending value is, that's your translation up or down, that k value. If there is no k value, then you have no vertical translation. Now, taking a look at a. The a value is going to tell us 4 things. First of all, if a is negative, you have a reflection across the x-axis, and it would look something like negative x squared. If x is negative, that means we have the negative inside the parentheses with the x, and that would be a reflection across the y-axis. Vertical stretch occurs when your value for a is greater than 1. So we're not talking about that negative sign. That negative sign is not going to come in play here. We're just talking about the value of a. So if the value of a is greater than 1, such as 2x squared, we have a vertical stretch. You have a vertical compression if that value is between 0 and 1, such as 1/2 x squared. Now be careful, because just because it's a fraction doesn't mean it's going to be a compression. You can have a fraction that is greater than 1, such as 3/2. In that case, it will be a stretch because a is greater than 1. So be careful. Just because you see a fraction does not mean that it's a compression. That fraction must be between 0 and 1. So let's identify the transformations that took place from the solid quadratic to the dashed quadratic in each of these graphs. So starting off with A, first let's take a look at where the vertex is. The vertex got moved to the right 2 units, so it's translated right 2 units and then translated down 3 units. For B here, obviously we have a reflection across the x-axis, but our vertex did not move. Now you notice that the dashed graph looks a little fatter than the solid graph. That's because we have been compressed. If the graph looks flatter, then we have compressed it. If it looks like it's been stretched or pulled, then we have a stretch. For C, we have a graph that was translated up. We also have a graph that was stretched, but it was also translated up 3 units. For D, we have a graph that was reflected across the x-axis. It was not stretched or compressed. It was translated left 3 units. Now let's identify the transformations that took place in these equations. I think it's a little easier to identify these things in equations than they are in graphs. So let's start from left to right. We have a 3 out in front, a leading coefficient. That's our a value. It's greater than 1, so we have a vertical stretch of 3. Our x squared is just our parent function. The only thing that's happening to our parent function is multiplied by 3. So that is our only transformation. For b, we have a minus 2 on the inside. That's our k value. Our k value is 2, telling us that we are translated to the right 2 units. And then we have our plus 3 on the end, which means that we're translated up 3 units. For c, we have a negative out in front, telling us we're reflected across the x-axis. And we have a plus 5 inside the parentheses, so that's a negative 5 for our h value, meaning that we translated left 5 units. For d, we have a negative sign leading, so we're reflected across the x-axis. We have a plus 1 on the end, so that means we are translated up by 1 unit. And don't forget, I forgot this one, we have a 2 in front of that x squared, so we were stretched by a factor of 2. For e, we have a leading coefficient of 1/4. It's positive, so we're not reflected, but it is less than 1, so we have a compression of 1/4. We have a minus 3 inside the parentheses, so our h value is 3, meaning we were translated right 3 units. And then a negative 6 on the end tells us we're translated down 6 units. 1/2 out in front tells us we're compressed by 1/2. Minus 2 on the end tells us that we're translated down 2 units. Now, the thing that's helpful in knowing how transformations work on the parent function is being able to write a quadratic function given its graph. So we're going to be able to look at a graph of a quadratic function of a parabola, and we're going to be able to write what the equation for that graph is. So to write a quadratic function in vertex form, identify the coordinates of the vertex and some other point on the parabola. Plug in the vertex for h and k and the point for x and y. And then we're going to solve for a. Finally, plug a, h, and k back into the vertex form without the point plugged in for x and y, and that will give you your function. So let's write the quadratic function vertex form for each of these graphs, starting with a. We need to identify the coordinates of the vertex. So the vertex is 1, -2, and then some other point. It can be any point that cleanly goes through the coordinate plane. So here I've just chose 3, 2 as a point that we can use. Then you're going to take vertex form. You're going to plug in your x and y and your h and k. And then you're going to solve for a. And we get a equals 1. Now you can take that a value, plug it in. We don't have to write it because 1 times anything is just that anything. And so we'll plug in our vertex at h and k to get our final function, leaving x and y alone. For b here, again, our vertex, start with that, -3, 0. Find another point. In this case, I'm using -5, -4. Another point you could have used was -1, -4. Or -2, -1, -4, -1. All of those would have worked. We take our vertex form, plug in our h and k, plug in our x and y, and then we're going to solve it to get a equals -1. So we can write that negative out in front, plug in our h, k is 0, so we don't have to write plus 0 on the end, and that is our function. For this one, our vertex is at the origin, 0, 0. Another point that we can use is 1, 2. So let's plug that in. Our h and k are both 0, so we'll plug those in. X and y being 1 and 2. And we simplify this one fairly quickly to get x, or I should say a equals 2. And then plug 2 in for your a. You plug in your h and k, which are both 0, so you just end up with 2x squared. For D here, we are going to get our vertex and another point, and then we are going to plug everything in like we've done before. Solve for a to get a equals -1. And then plug in your a, h, and k to get your final result, -x squared plus 3. That is the function or the equation for that graph.
Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.